it's time to do another physics problem. A car starts from rest and travels for 5.2 seconds with a uniform acceleration of 1.7 meters per second squared. The driver then applies the brakes, causing a uniform acceleration of -2 meters per second squared. The brakes are applied for 3.1 seconds. How fast is the car going at the end of the braking period? So again, we want to try to picture this in our mind, and we've actually got two different things going on here, which is going to be important. So first of all, think about that. You're in a car, you're at rest, and you travel for 5.2 seconds with a uniform acceleration of 1.7 meters per second squared. So again, that means that the car is beginning to speed up, and then you apply the brakes. That's going to be the second part of our problem. You apply the brakes and you actually have a deceleration, and you actually come to a complete stop. Actually, how fast is the car going at the end of the braking period? So we actually don't come to a complete stop. We're slowing down, and then we want to find how fast are we going after 3.1 seconds. So let's go ahead and take that idea and put it in the form of a diagram. So there's our car. It actually accelerates or gains velocity during the first segment. So it starts out at 0. And the first segment takes place over a time of 5.2 seconds. And we're accelerating at a rate of 1.7 meters per second squared. And then here, let's say here, we apply the brakes and begin to slow down. So I'm going to go ahead and draw another diagram. And we don't know how fast we're going. We don't completely stop. Oops, I just said we don't completely stop. We don't completely stop. So we actually want to find out how fast we're going. And the amount of time that passes here is 3.1 seconds. And the acceleration here is -2.3 meters per second squared. All right, so this is our diagram. This is all our known and unknown information. Now we just can't go from here to here in one equation. There's two different things going on. There's two different accelerations taking place. So we're going to have to break this problem up into two different parts. Part one, the car is actually speeding up. So we're actually gaining 1.7 meters per second of velocity each and every second. Then we apply our brakes and we're actually losing 2.3 meters per second of velocity each and every second. We're going to do that for 3.1 seconds. We want to know how fast are we actually going. All right, so let me go ahead, since I want to know this, I'm going to focus on this part of the problem right there. I'm going to focus on that. And the equation, obviously I need an equation that's got velocity final in it. So what I'm going to do is I'm going to go ahead and I'm going to consider this equation. Average acceleration equals change in velocity over time. We're going to go ahead and expand this. Average acceleration equals the final velocity minus the initial over time. You can see the final velocity. That's what I want to find right there. I know the time, I know the acceleration, but I got a problem. I don't know the initial velocity. Now remember, I'm talking about this right here. So the initial velocity would be that right there. And I don't know what that is. But I know if I can solve for that, this problem's done. So I'm thinking to myself, the initial velocity for this is actually what? The final velocity for this segment or this leg of the problem. If I can find the final velocity for this problem, I can then take that final velocity and substitute it in for the initial velocity of this problem. So let's go ahead and do that. See if that works. So again, I'm going to use the same equation. Just so happens that works out in this instance. Average acceleration, change in velocity over time, final minus initial over time, and let me go ahead and substitute in. I know the acceleration, 1.7 meters per second squared. The final velocity, that's what I'm actually looking for. I'm looking, that final velocity for this is going to equal the initial velocity for that. So final velocity, I'm looking for that, minus the initial, which is 0. And the time is 5.2 seconds. So I'm going to go ahead and substitute in and solve. And my final velocity turns out to be 8.84. 8.84 seconds. Whoops. Meters per second. Now I don't want to round off here because that's not my final answer. So I want to take this unrounded off number and I want to put it in for my initial velocity here. So let's go ahead and do that. Here the acceleration is negative. Notice the velocity is positive, but the acceleration is negative in the opposite direction. So whenever the velocity and the acceleration are in the opposite direction, slowing down. All right, let's go ahead and substitute in. Negative 2.3 meters per second squared equals the final velocity. Hey, I'm looking for that. The initial, again, that's the same as this final velocity, so I'm going to stick this number in because that final velocity is the beginning velocity of the next segment. So 8.84 meters per second over the time. In this case, it was 3.1 seconds. And my final velocity turns out to be 1.71. So 1.71 meters per second. And again, if you're using significant digits, you'd actually round off to 2. So we'll round it off to 1.7 meters per second. And go ahead and put a box around that answer. Now we also got part B that we want to do. So part B is how far has it gone from the start? So how far has it gone from its start? So we're starting here, and I want to find this entire distance or displacement. So again, two different things are happening here. So I got to be careful. I can't just find it all in one equation. What I'm going to do is I'm going to find the displacement from here to here, and then I'm going to find the displacement from here to here, and then I'm going to add those two together. So let's go ahead and do that. I'm going to go ahead and erase this. So I got room to do part B. Now again, I'm looking for the displacement. I guess I'll go ahead and write that down. We'll call that x1. And then the displacement from here to here, I'll call that x2. So I'm looking for those two displacements, and then I can add them together. Right, so the equation, obviously the equation I want has to have an x in it. It has to have displacement. So that narrows it down. And then I also want to use an equation where the rest of my information can be used. So velocity final squared equals velocity initial squared plus 2ax. I'm looking for this. I know the acceleration. I know the initial velocity. And remember, I found the final velocity in part A. I found that. So I'm going to use this. Remember, I'm talking about this, so I'm going to use this final velocity. So let's go ahead and substitute in. So I've got 8.84 meters per second squared. The initial velocity is 0 plus 2. The acceleration is 1.7 meters per second squared. And then I'm looking for the displacement. So when I do the math here, right, I'm going to square that and divide that into it. I end up with 22.984. So 22.984 meters. We'll call that x sub 1. And then I'm going to do the same thing over here. In fact, I can actually use the same equation. So let's go ahead and do that. velocity final squared equals velocity initial squared plus 2ax. All right, so now my final velocity, in fact, that was the answer to my last problem, and it's going to be, final velocity was 1.71. So I'm going to go ahead and put that in, 1.71, that was my unrounded off number. I'm going to square it. My initial velocity is actually this velocity right here. Remember that velocity right there, 8.84 meters per second squared plus 2. My acceleration is negative 2.3 meters per second squared. And then my displacement, that's what I'm looking for. All right, in order to find this, we've got to square that, we've got to square that, and then you want to take this minus that divided by that, and that's going to give me my displacement. And my displacement should be positive because it's in the positive direction. So when I take this minus that, that's going to give me a negative number. And then when I divide two negative numbers, I'm going to end up with a positive x. And when I do that, it turns out to be 16.35. So 16.35 meters. We'll call that x2. When we add those two together, we're going to end up with 39.34. So 39.34 meters. And again, I'll just round off to two significant digits. So I'd round off to 39 meters. So there we go. A good two-part problem.